Welcome to Lecture 17, which deals with oscillatory motion. Lecture 17 is the first of Section 2, which I've titled Wiggles and Flows because it applies the ideas of Newtonian mechanics to more complex motions, the oscillations of oscillatory systems that we'll deal with in this lecture, waves in the next lecture, and then 2 lectures on the motions and statics of fluids. Now, we've seen in the previous lecture that systems tend naturally to find themselves in equilibrium states, states where they're at the minimum points in their potential energy curves. If they weren't in those states, they would quickly get into them because they would be unstable. But what happens if we disturb a system that's in its stable equilibrium state? Well, by definition of stable equilibrium, it's going to eventually return to that equilibrium. But systems have inertia, so they tend to overshoot their equilibrium position, and what happens is they go into a back and forth oscillatory motion. And this is a really universal phenomenon throughout the universe. Some stars undergo actually major oscillations, which makes them pulsate and appear to vary in brightness. They do vary in brightness. Skyscrapers wave back and forth and undergo oscillatory motion. Bridges do. I'll show you at the end of this lecture a disastrous application of that. Systems from the size of molecules up to the size of stars, including systems at the human scale, tend to undergo oscillatory motion if they're disturbed from equilibrium. And in this lecture, we want to explore that oscillatory motion in some quantitative detail. Let me begin by giving you a couple of simple examples of oscillatory motion with some straightforward, simple systems. So here I have the big yellow ball. We've seen it before. It's hanging on a spring. And I'm going to give it a little displacement from its equilibrium position, and it overshoots that equilibrium, and it goes into an oscillatory motion, an up and down oscillatory motion, in this case, driven by the spring. And we've talked about that before in terms of energy transfers. We want to focus more on the actual motion in this lecture. Here's another example. I've got a tennis ball hanging on a string. I pull it aside from its equilibrium position, which is to be hanging vertically, and it also undergoes some kind of oscillatory motion, in this case, a back and forth arc-like swing because it's a pendulum. We want to understand how to quantify these oscillatory motions. So how do we do that? What do we do to describe oscillatory motion? Well, we have quantities related to time. One quantity is the period. We'll give it the symbol capital T. It's the time for one complete oscillation cycle. In the SI system, its units are seconds. Our big yellow ball is bouncing up and down with a period of, maybe a couple of seconds, for example. The frequency is the number of oscillation cycles that occur per second. Its SI unit is cycles per second, which is given the name Hertz, Hz, but that means the same thing as a cycle per second. And since the period of that oscillation is about 2 seconds, it's going at about half a cycle per second, about half a Hertz. In fact, with the relationship between frequency and period is straightforward. The frequency is the inverse of the period and vice versa. So you can specify either one, and you've said what there is to say about the time behavior of that oscillatory motion. There's also space-related behavior, and the important space-related behavior is the amplitude, the maximum disturbance from equilibrium. So this ball is bouncing up and down, and if I grab a meter stick, I could measure how far it's moving from its equilibrium position, and it's a few tens of centimeters in this case. So those are the quantities we want to describe oscillatory motion. Now, it turns out that for a great many systems, the restoring forces, or sometimes torques, that tend to restore the system to equilibrium happen to be proportional to the displacement. I'll show you more rigorously mathematically in a few minutes why that is. But I want to emphasize how universal that property is. From molecular systems to the astrophysical scale, it's very frequently the case, at least if we make relatively small disturbances from equilibrium, we end up with forces that tend to restore the equilibrium that are proportional to how far we have moved from equilibrium. And if that happens, we end up with a special kind of motion called simple harmonic motion. It's the motion that occurs when the restoring force or torque is directly proportional to displacement from equilibrium. It's ubiquitous, as I've indicated. It's everywhere from molecular to astrophysical systems. And it is characterized by a very simple relationship between the position of the object undergoing this motion and the time. And a very important feature of simple harmonic motion, which does not necessarily apply to more complicated oscillatory motions, is that the frequency and period are independent of the amplitude. So I can make this ball, for example, undergo large amplitude oscillations or small amplitude oscillations. And if, in fact, the restoring forces are proportional to the displacement from equilibrium, then the amplitude will not affect the period or frequency. We already saw for springs that they produce a force that's directly proportional to their stretch. And that means the paradigm system for simple harmonic motion is a mass on a spring, as you can see in the video clip here at the bottom, where this mass is oscillating back and forth on a spring. So the spring is sort of the paradigm of simple harmonic motion, and I'll be talking largely about simple harmonic motion caused by springs, at least at first. But you can think of pulsating stars, molecules vibrating, skyscrapers swaying as examples of systems that are behaving in a spring-like fashion and undergoing simple harmonic motion. Well, we're getting mathematical in this course, so let's take a look at how we get to simple harmonic motion. So here's a mass spring system. Newton's second law tells us that F equals ma for this system. We know that when we're dealing with a spring, it produces a force minus kx. I've put the minus sign there because if I stretch the spring a distance x, the force is the other way, tending to pull back. That's what the minus sign is telling us. K, remember, is the spring constant. It tells us how stiff the spring is. It's the number of newtons we get for every meter of stretch. So the spring force is minus kx. Here we go. Our mass spring system is oscillating back and forth. This is a horizontal mass spring system. My big ball is a vertical one, but same idea. Acceleration is, of course, the rate of change of velocity. So this a that goes in Newton's law can be written as the rate of change of velocity. Velocity, on the other hand, is the rate of change of position. So the acceleration is the rate of change of the rate of change of position. And if I were to write Newton's law for this system, I would write minus kx. That's the physical forces acting, the things that go on the left side of Newton's law. It is equal to the mass times the rate of change of the rate of change of position. Now, I'm not going to go any further mathematically with that because the way to write that more compactly would involve the symbolism of calculus, and the way to solve that equation, which is the equation that describes the motion of a system like a mass on a spring, involves calculus. In fact, it involves differential equations. So unless you've had a course in differential equations, you probably wouldn't know how to solve that equation. So I'm going to just give you the solution via calculus. It's that x, the position of the object as a function of time, is some constant a, that's the amplitude of the motion, that's how far it gets from equilibrium, times the cosine, the trig function cosine, of omega times time, where omega, introduced that before for angular velocity, is quite closely related actually, is the so-called angular frequency, and it's given by the square root of the spring constant divided by the mass. So that says the frequency will be higher if the spring is stiffer, k is bigger, and the frequency will be lower if m is bigger. Makes sense, m is in the denominator, because if m is bigger, we have more inertia, the system will be more sluggish. So this frequency is beautifully independent of the amplitude in simple harmonic motion. So let's take a look at that equation in a little more detail and see how we can understand it. So anatomy of this equation, x equals a cosine omega t. What does that mean? X is the position of the mass m as a function of time, and x equals 0 we're taking to be the position of the spring when it's unstretched, so it's in equilibrium. It gets compressed in one direction, stretched in the other direction. A is the amplitude. It's the maximum value x ever takes on. Because cosine swings between plus and minus 1, x swings between plus and minus a. Omega is the angular frequency, and t is time, and I've used the cosine because I've chosen to make time be 0 at the maximum displacement. So, for example, I pull my ball away from equilibrium, and I let go, and I call that time t equals 0. That's why the cosine function appears there. So here's kind of a picture of that motion as a function of time. We start out at A. We go through a full cycle of the cosine. That's one cycle. That takes time t. At the end of the cycle, the time is the period, big T. The quantity omega t, the argument of the cosine function, has gone from 0 at the beginning to 2 pi at the end. The position swings between a and minus a as the motion progresses, and then it simply repeats. This angular frequency is not something familiar to you. It has units of radians per second, or just seconds to the minus 1. The regular frequency in hertz, because there are 2 pi radians in a full circle, the regular frequency in hertz is smaller by a factor of 2 pi. So it's omega over 2 pi. And the period in seconds is 2 pi over omega, or 2 pi times the square root of m over k, because omega was the square root of k over m. And again, a full cycle occurs as omega t increases from 0 to 2 pi. Now that's a lot of math. But don't take my word for it. Let's just put that equation up here, and let's do an experiment that shows that indeed that is the equation for the motion of a mass on a spring. Okay, so here I've set up a little demonstration using our clever Pasco motion sensor. I've now got it right below the yellow ball, pointing upward, looking at the yellow ball. It's connected through this cable to my computer, and the computer will record the data, the position as a function of time, and display it for us on the big screen. So let me get started. First thing I'm going to do is press the start button, because I want you to see that initially it will take data showing that the ball isn't moving, and then I will displace the ball and will set it into its simple harmonic motion. So here we go. Okay, started out with no motion, I displaced it, and now we're getting that beautiful, regular sinusoidal motion, characteristic of simple harmonic motion. That is a beautiful proof, or at least an experimental verification, that the motion when the object is subject to a restoring force proportional to its displacement from equilibrium, that motion is sinusoidal in shape as a function of time. You will notice, if you look carefully, by the way, that the amplitude is decreasing slightly. That's due to loss of energy to friction. It's very slight in this case, but it's there, and we'll talk about that more at the end of the lecture. So, because we aren't doing calculus proofs, I wanted to verify experimentally that, in fact, that equation involving the cosine of omega times time is, in fact, correct. We could also look at this graph and tell that the amplitude was went from about 0.8 meters down to about 0.5 meters, so the amplitude was about 30 centimeters, and we can also measure from this graph the period. I had guessed before that it was about 2 seconds, and indeed that's about correct. Here we are at about 3.5 seconds, and here we are at about 5 seconds, so it's more like 1.5 seconds for the period of that simple harmonic motion, and that period stays constant because the period is independent of the amplitude. Well, simple harmonic motion in a mass spring system clearly involves energy. There's energy of the mass as it moves, that's kinetic energy. There's energy of the stretched spring, that's potential energy. We've already seen, in fact, that energy is interchanged continually between kinetic and potential energy in a mass spring system. But now we're focusing on that in the context of simple harmonic motion. So here we have this movie we've seen before of a simple harmonic oscillator, a mass spring system oscillating horizontally, and we see the bar graphs showing the amount of energy that's potential and the amount that's kinetic, and they're continually exchanging energy, and so they're going back and forth. If we took snapshots at individual points in time of what's going on, we'd find the mass started out as in its extreme stretched position, the greatest potential energy, no kinetic energy. As it moves inward, there's a mix of potential and kinetic energy. Eventually, it goes whizzing through its equilibrium position with the highest speed it's going to have. The energy is all kinetic at that point, and there's no potential energy. And then the spring begins to compress, and the energy builds up as potential energy more and more. Eventually, it's all potential energy when the spring is compressed as much as it's going to be, and then the spring starts pushing the mass back out again, and the cycle repeats. And again, if there's no mechanism of energy loss, no friction or anything, that will continue basically forever. If we were to plot a graph as a function of time of kinetic energy and potential energy, each of them would be a sinusoidal graph, and that's because each of them goes like the square of either the position in the case of the potential energy or the velocity in the case of the kinetic energy, and the square of a sinusoidal function is itself sinusoidal. So we see two sinusoidal functions, but they're out of phase in the sense that the potential energy peaks when the kinetic energy goes to zero and vice versa. And if you were to add up at any point in time the values of the kinetic and potential energy on that graph, and there were no losses at all, you would find the total energy was that solid horizontal line at the top indicating that the total energy is unchanged. So that's an energy consideration in simple harmonic motion. Now, remember that simple harmonic motion occurs when the restoring force is directly proportional to the displacement. And you might say, well, at least in terms of my discussion so far, that's certainly about springs. But what about other systems? I've been arguing that stars and molecules and skyscrapers and bridges and cars with their suspensions undergo simple harmonic motion. I want to show you now why simple harmonic motion is really ubiquitous. And let's do that mathematically here on the big screen. So why is simple harmonic motion ubiquitous? We can understand that by thinking about the energy in simple harmonic motion. The potential energy of a mass spring system is the potential energy stored in the spring when it's stretched or compressed a distance x from its equilibrium. U is a half kx squared. We've seen that before. We worked that out by looking at the area under the diagonal force distance curve for a spring system. I'm claiming that this is universal in the following sense. The fact that the potential energy is proportional to the square of the displacement, and for a spring, its proportionality constant is the spring constant k and the 1/2, but that means mathematically that any other system in which the potential energy is a quadratic function of whatever measures the displacement from equilibrium, position, angle, whatever, then mathematically that system will also undergo simple harmonic motion. So any system whose potential energy curve is quadratic, at least in the vicinity of a minimum, because that's where we'll find stable equilibria, any such system is going to undergo simple harmonic motion. The potential energy is parabolic or quadratic in the displacement, and it depends on x squared, and that's another way of characterizing simple harmonic motion. Simple harmonic motion, yes, it's caused when the force that tends to restore equilibrium is proportional to the displacement, but another way of putting it is it occurs when the potential energy is parabolic or quadratic in the displacement. Now, here's the big story. Here's some complicated potential energy curve for some complicated system. I don't know what it is, a skyscraper, a star, a molecule, something. It's got all kinds of wiggles and valleys and things. Here's displacement, here's potential energy. This system could be in a stable equilibrium at the bottom of that valley. And if you disturbed it slightly, it would oscillate back and forth. Now, this could even be a roller coaster. It isn't. It's a potential energy curve for an arbitrary system. But if it were a roller coaster, I'd put a little car in there, it would go back and forth. Here's another little valley I could put it in. And that's probably not a valley, but there are two valleys there and there. And here's the point. Near the minimum of a curve of any sort, with very few exceptions, mathematically, those curves are best approximated by parabolas. There's something called Taylor expansions, which describe how you write a function, an arbitrary function, in terms of other simple functions. And it turns out that when you do that for a U-shaped kind of structure in any kind of mathematical function, the best fit to it is a parabola. So as long as we're down low in here, these best fit parabolas that I've drawn in white represent pretty good approximations to the shape of the curve, at least if I don't give it too much of a displacement. By the time I'm over here, they're not agreeing very well. But down in the bottom, they agree. And what that means is almost any system which is in a stable equilibrium, that is, in a minimum in its potential energy curve, is going to undergo simple harmonic motion. And that's why simple harmonic motion is ubiquitous. That's why I argue it happens throughout the entire universe and becomes a very, very important thing for physicists to study. Well, let's look at some other systems that undergo simple harmonic motion. Over here, I have a weighted tennis ball hanging on a string. If I displace it somewhat from its vertical equilibrium position and let it go, it swings back and forth like a pendulum. Its angular position or its position along the horizontal direction, they're almost the same for small arcs, varies sinusoidally with time, just like the position of the vertical mass spring system. That's another example of a simple harmonic oscillator. And let's do a little bit with the mathematics of the pendulum. We won't go through all the details, but let's take a look on the big screen at some things that will help us to understand the pendulum. So the pendulum exhibits simple harmonic motion for small amplitude swings. And I want to emphasize that. If I really swung that pendulum way out, it would no longer be simple harmonic motion. It would be more complicated motion, and its period would no longer be dependent or be independent of its amplitude. But for small amplitude swings, like the arc I started there or the arc shown here, a parabolic fit to that circular arc, it's a circle, not a parabola, is very, very close. And so for small swings, the parabola approximates the circular arc, and therefore the pendulum undergoes simple harmonic motion. And I'm not going to derive this, but it wouldn't be very hard to do, that the period of that motion is t equals 2 pi times the square root of L over g. Now, if you compare that with the period of the mass spring system, the period of the mass spring system was 2 pi square root of m over k, mass over the spring constant. The bigger the spring constant, the shorter the period, because the more vigorous the spring. Well, in this system, gravity plays the role of the spring. It's what provides the restoring force. It's what pulls the pendulum back toward its equilibrium. So it appears in the same place in the equation that the spring constant did in the equation for the period of the mass spring system. On the other hand, in the mass spring system, the mass is what had the inertia, and it went upstairs in the fraction in the square root because it provided the inertia. The bigger the mass, the slower the oscillations. Well, the same thing is true here, but it's the length of the pendulum string that provides that kind of inertia. Pendulums have been historically important. Galileo first thought about them. He developed pendulum clocks, have used pendulums for years to work out their timing, to determine a fixed time. And we can, in fact, look at a period of a pendulum. Suppose we wanted to make a pendulum with a 1 second period. Well, we could solve this for L. You have to undo the square root. That squares the 2 pi to 4 pi squared. The g comes up, the t gets squared, and L becomes gt squared over 4 pi squared. G is 9.8 meters per second squared. We want 1 second for the period, divide by 4 pi squared. That comes out about 1/4 of a meter, or about 10 inches. And so our pendulum that we have here, which has a string length of, about a meter, is got quite a bit longer period. It's a period of much more than a second. It's several seconds for that pendulum. There are other systems that undergo pendulum-like motions. For example, our dancer over here, whose center of mass we determined, she constitutes what's called a physical pendulum. If I set her swinging, she goes back and forth in a pendulum-like motion whose period is rather more complicated to determine. It involves an effective length from the pivot to her center of mass, and it also involves her rotational inertia, because how well she pivots depends on how her mass is distributed. Another example of a physical pendulum is this ring that was in that race down the ramp in an earlier lecture. If I get it swinging, it will undergo also simple harmonic motion. Finally, my big yellow ball, I put a piece of red tape on it to indicate that if instead of letting it bounce up and down, I give it a little twist like this, it will undergo what's called torsional oscillations. It's pivoting back very slowly. And as the spring gets tension back and forth, and so on. And that motion will continue for a long time until friction damps it out. That's called a torsional oscillation. In the days before quartz clocks and quartz watches, the timing of a watch was done by a little balance wheel with a spring that underwent torsional oscillations. They've been replaced by the simple harmonic motion now in little quartz crystals that are oscillating 32,768 times a second, and that number is divided down 16 times to give you 1 second period, which then drives the mechanism of the watch. So there's a look at some other simple harmonic oscillators. I'd like to look now at some more far-out versions of simple harmonic oscillation, that is, molecular oscillators. So let's take a look at what happens when we talk about molecules. Chemists actually talk about the spring constant of a molecule. Let's look at why they do that. So here is the potential energy curve for a pair of hydrogen atoms. We talked about that before because that was going to give us a minimum in the potential energy curve, and that's where the two atoms were going to sit when they formed a stable H2 molecule. So we've seen that graph before. Here's a kind of picture of the molecule, and a chemist might literally picture the molecule as the two hydrogens stuck together by a spring. There isn't a real spring there. What there is instead are the electrical forces and the repulsion of the nuclei and attraction of electrons and various other things that result in a spring-like behavior, at least for small disturbances from that equilibrium. And again, you can see that because in the potential energy curve, if I try to fit a parabola to the bottom of the curve, it's a pretty good fit right near the bottom. And so that means this thing will undergo simple harmonic oscillations like our mass spring system. Now, a caveat here. You really need quantum mechanics to treat this accurately. This is a classical description of something that is not entirely classical because it's too small. But we're getting at the big idea of it. And so if I set that thing into motion, it's going to oscillate like a mass spring system. It's sort of like two mass spring systems connected. That's hydrogen. That's a pretty simple molecule. The things get much richer with more complicated molecules. Here's carbon dioxide, carbon with two oxygens. It has several ways it can oscillate. One way is like that, with the two oxygens oscillating independently as simple harmonic oscillators. Another way is for it to oscillate asymmetrically, something like that, with all of them set into motion. And a third way is for it to oscillate in a nonlinear fashion, so it's no longer in a straight line. CO2 is normally a straight line molecule oscillating like that. And it's those many different modes of oscillation, simple harmonic motion, that's available to the CO2 molecule that makes it absorb many different frequencies of infrared radiation. It turns out the frequencies are such that it's infrared radiation it absorbs. And that's ultimately what's responsible for human-caused global warming. We put carbon dioxide molecules in the atmosphere. They go into all these complicated simple harmonic motions, and in the process they do absorb energy from the outgoing infrared radiation. And that's basically what keeps the heat in and causes global warming. So there's a sort of microscopic view in terms of simple harmonic motion at the ultimate cause of global warming. Okay, so I've indicated earlier that these simple harmonic motions tend to damp out. Earlier I started that pendulum going, and it's still going, but not very much. My dancer is still moving, but just barely. This ring is still moving, but just barely. And my big ball is just barely oscillating a little bit. Again, if I set the ball oscillating, the amplitude of that oscillation will eventually die out, and it's dying out in this case because of losses in the spring. As it stretches, it heats up a little bit and loses some energy, and losses to air resistance as that big ball goes up and down through the air. That process of losing energy is called damping. And if you want to keep an oscillating system oscillating, it's kind of a nuisance. But there are many cases where we really like oscillating systems to be damped. Let me give you one important example. When you're driving down the road in your car and you hit a pothole, the worst thing you want to have is to have the wheel of your car coupled directly to the driver's seat so you feel that sudden shock of the pothole. Well, it isn't coupled directly. There are springs that support the body of the car, the passenger compartment, and separate them from the wheels. So if there were just those springs and you were to hit a pothole, the car would start bouncing up and down in simple harmonic motion until it gradually, over time, damped out. And you may have occasionally seen a car going down the highway kind of doing this. That's because another critical component in that car is gone. That component is the shock absorber. And the shock absorbers work with the springs, and they have a piston that moves through a liquid, and it's hard for it to move. There's viscosity, and that damps out the motion of the springs. And so the idea is you hit a pothole and you absorb that shock briefly. The springs allow the wheel and the car to move relative to each other vertically, but you quickly damp it out with the shock absorber. That's called a critically damped system. You damp it out in the shortest possible time. And so if we were to look at what damped systems look like, here's a graph of 3 different simple harmonic motion systems. The one marked A shows an oscillation, a very clear oscillation, although it's clearly damping out pretty quickly. It's not like my ball. Well, my ball has damped out now, but it's gone through many oscillation cycles before its amplitude got reduced. In this case, we damp out in a few cycles. That's fairly heavily damped. But case B is the case of critical damping. That's where the damping is just right and the system stops, never even undergoes an oscillation. It quickly comes down to its equilibrium position again. And that's what you want for some systems, like a shock absorber. If you put too much damping, there's so much friction, the system moves too slowly, and then you get curve C, which is called an overdamped system. It isn't damped optimally because it takes longer for it to come back to its equilibrium position. Well, let me end with one other aspect of simple harmonic motion or oscillatory motion in general. Oscillating systems tend to have a frequency they would like to oscillate at. And if you happen to hit them with something at that frequency, example, if you're pushing a child on a swing and you push every time the child comes back, you're feeding energy into the swing at exactly the frequency it wants to go at, and so it builds up large amplitude oscillations. That phenomenon is called resonance. And I'm just going to give you a couple of very dramatic examples of resonance here at the end. But don't go away, because I have a challenge for you that I think you'll enjoy. But let's look at resonance first. So here are a couple of movies of famous events involving resonance. The one on the left is the destruction of the Tacoma Narrows Bridge, which was opened in 1940 in Washington State, and it collapsed 4 months later due to resonant oscillations that were ultimately triggered by the wind blowing across the bridge structures. And it's a very dramatic event, and there were wonderful videos taken of it, including passengers coming out of a car and staggering down the center line of the highway trying to get off the bridge before it collapsed, and he indeed succeeded in doing so. At the upper right, we see a situation in which a wine glass is being subject to simple harmonic oscillations of sound waves coming from a loudspeaker, and as those oscillations build up, you can actually see the rim of the wine glass vibrating, and eventually, poof, it blows apart. Opera singers have been known to shatter wine glasses with their voices, although this is a more carefully staged experiment in a physics laboratory using sound coming from a loudspeaker. So resonance is an important phenomenon when you design buildings, when you design bridges, when you design loudspeakers, when you design any kind of structure. You would like to avoid resonance at frequencies that it's likely to be subject to. Well, I promised an interesting challenge. This challenge is for anybody who's wondered what would happen if you were to drill a hole right through the center of the Earth. So take a look at this challenge, and if you really want to get mathematical, it's not that hard to work out, although it takes a little bit of thinking to figure out the analogs with what I've been talking about here. So here's the challenge. Imagine drilling a hole straight through Earth's center and out the other side. And we'll neglect air resistance, which is not a very good approximation here, but we'll do that. I would like you to come up with an argument that if you drop an object into that hole, it will fall right through the center of the Earth, and it will come out to the surface on the other side, and it will go back and forth, and that the motion will be simple harmonic, and I would like you to find a numerical value for the period of that motion. Assume that the Earth is a uniform solid sphere, which is not quite the case, and if it were, the gravitational acceleration inside the Earth would be what it is at the surface, scaled by how far down you go into the interior. So it's 0 at the center, and it goes linearly upward toward the surface, where g surface is, of course, 9.8 meters per second squared. Earth's radius, RE, is 6,370 kilometers, and r, lowercase r, is going to be the distance from Earth's center. So pause, work that challenge. It'll take you a while. I'll give you the answer. Okay, here's the answer. The answer is, the formula for the period is 2 pi times the square root of the Earth's radius over g. Looks awfully like the period of a pendulum, doesn't it? That works out to 84 minutes, and it turns out to be exactly the same period as a spacecraft in low Earth orbit, surprisingly. Actually, not so surprisingly. Think about that.